Experience at Foster Wheeler is in the design of fossil-based power and chemical generation plants. His experience also spans feasibility studies, basic design and detailed engineering phases of several worldwide projects. His particular area of specialization is in the design of power and chemical plants with carbon capture and sequestration. I request Mr. Mancuso to guide me the exchange.
Thanks for the nice introduction. And as she said, the main objective of the presentation today is talking about how to minimize CO2 removal penalty in oxy-combustion plants. Just to start, for those of you who are not familiar with Foster Wheeler is a global engineering, procurement, construction contractor, but also is a power equipment supplier. And we are a Nasdaq-listed company, and with our headquarters based in Reading, UK. And we have permanent offices in 30 countries, and with over 13,000 employees in the world. We've been in this business for a while, because we've been in this business for more than 115 years. And what is important to say is that we have two main business groups. One is related to the global engineering and construction group, where I belong. And the other one is the global power group. The global power group is the equipment supplier for the power sector. Today I want to report you the results of a study that Foster Wheeler is completing now for IEA GHG. But today we had a very nice introduction of the company from Prachi, so you know quite well what is IEA GHG. What's the background of the work we have made for IEA? In the past years, IEA GHG undertook a series of studies on performance and costs of coal-fired power and hydrogen plants, with and without CO2 capture, and for the plants with CO2 capture based on the three leading options, POS, pre, and oxy. But following the significant technological advances and also the substantial increase of plant costs during the economic crisis, IEA decided to undertake a completely new study to provide an up-to-date assessment of these plants. So, final report will be issued very shortly. What are the objectives of this work? This study aims to provide baseline for subsequent studies on other capture processes and capture in industries other than power and hydrogen generation, and covers different plant types, all the three leading technologies. But today, let's focus on the oxy-combustion supercritical pulverized coal plant with cryogenic purification of the flue gases. During our work, we had a lot of support from many technology suppliers and licensors, which provided an invaluable support for the success of the study. These are listed in alphabetical order in the slide. As I said, we had a lot of support from them, and which added a lot of value to our work. These are the key topics of my speech. So I will go through a very general introduction of the oxy-combustion process. Then I will show you what are the design basis for our study. I will go through the key design features of the plant. I will explain you the main performance, the economics, and I will ask with some conclusions. So, let's start. For those of you who are not very familiar with the oxy-combustion processes, this is a schematic representation of the process. So, what is the key difference with respect to the standard plant? In this case, you have your feedstock, for example, coal, and the combustion is not made with air, it's made with oxygen. And the oxygen is coming from a standard air separation unit, which makes the separation of oxygen and nitrogen from the air by using a standard cryogenic technique. So, when you have combusted the coal with oxygen, the key difference with respect to the standard process is that the flue gases are composed of CO2 and water, so there is no nitrogen in the flue gases. And that means that after cleaning the flue gases from convention, from the ashes and the SO2, then you can go to a cryogenic, to a compression purification unit, which makes the separation of the CO2 from the other bad gases, which are mainly some nitrogen, residual nitrogen and argon. One key difference with respect to a standard process is that, as we said, there is no nitrogen coming from the air, and that means that the volumetric flow in the boiler is significantly lower than a standard process which makes the combustion with air. And that's the reason why you need some recycled flue gases at the inlet of the boiler in order to keep volumetric flows similar to a conventional boiler, but also to control the firing temperature, because without the nitrogen, the risk is that you can go very high with the combustion temperature. So the recycled flue gases allows you to control the combustion temperature of the process. We said you need oxygen, but I don't want to spend too much time on the oxygen, because oxygen is, the ASU is a very well-known technology. This is the slide coming from air products. So basically you take the atmospheric air and you have an initial phase where you have a compression of the air using main air compressor and boost air compression. Then you have pre-cooling and pre-treatment, basically to remove the water from the air. And then you go to a cold box, to a cryogenic unit here, which makes the separation of the oxygen and the nitrogen. And then the oxygen can also be easily stored at your plant. So we say that flue gases are mainly composed of CO2 and water. And when you want to capture the CO2, you have different options. You can either take the flue gases as they are, basically, so you can go to a straight compression. You're removing basically the water for condensation. But in that case, you have CO2 whose purity is in the range from 90 to 92%. Otherwise, there are other options if you want to achieve higher purity CO2, and you can make a cryogenic purification. And you have different options. You can either use a conventional refrigeration cycle, or you can use an auto-refrigerated cycle. And I will explain you this cycle in a minute. Also, you have other options. You can include distillation columns in the flue gas treatment in order to have a very high purity and very high capture rates of the CO2. Where we are now with the oxy-combustion process. This is a slide which is coming from the latest conference on oxy-combustion, which was held in Spain. And just to summarize, oxy-combustion testing started in the 1980s, so a while ago. But and we've also had the first large-scale pilot plant, 35 thermal megawatts, was more or less in 1995. So a lot of time ago, and we had the first full chain demonstration plant 30 thermal megawatts, which was built and operated in Germany at the Schwarze Pumpe. This was 2008. As of today, we can say that we have at least six partner manufacturers available to supply their technology into the market. So they are quite mature and they're available to supply their technologies. Following the Schwarze Pumpe experience, there have been other pilot plants running in Europe and US. And here you can see an example. It is mentioned the LAC project in France, the FUEL project in Spain. And this afternoon, in the session this afternoon, I will go very deeply showing you a lot of details coming from the experience of the FUEL and pilot plant in Spain, which is using either the oxy-PC and the CFB power plant. And but now where we are today, so today there are several other projects and for a large scale. And I want to mention, someone has already mentioned FutureGen number 2, but there are also other projects. One is in China, another one is in UK, which is the White Rose projects, which are running very fast. And we do think that the target of having a large-scale oxy-combustion plant by 2020 is there. So it will be possible that at least one or two plants at large scale will be in operation by 2020. Okay, so if we go now back to the work that we have made for REA GHG, what are the key design bases we considered in our work? Okay, so the coal is an Eastern Australian bituminous coal, so it's quite a good quality coal. The sulfur content is in the range of 1.1. And what is important to say is that we considered the use of state-of-the-art technologies. So we considered one single boiler, large boiler, which allows the production roughly of 1,000 electrical megawatts. So this is the basis for the design of our case. Oxygen purity from the air separation unit going to the boiler was selected to 97%. And steam conditions are supercritical steam conditions, so to 270 bars and 600 degrees C, and for the single reheat was 60 bars and 620 degrees C. A few words regarding sulfur content. So, as I will explain to you, the issue with the sulfur from the coal is related to some corrosion issues into the boiler, not related to the emissions from the plants. And it was fixed to be not greater than 2,000 ppm within the boiler to limit corrosion in the boiler. CO2 capture, the capture rate is in the range of 90%. We also did a case of higher capture rate in the range of 98-99%. And you may see the purity requirement of the CO2. In particular, I want you to highlight that there was a requirement for the oxygen content of the CO2 up to a maximum of 100 ppm. CO2 conditions, 110 bars and 30 degrees C temperature. Regarding flue gas desulfurization, as I will explain you, we have considered several options, dry, wet, and many types of flue gas desulfurization, and when we choose the best one for our case. And we consider the installation either on the primary or the secondary recycle. So remember, we said that the recycle is very important and to control the temperature in the boiler. Regarding the compression and purification units, we had a lot of support from Air Products, and we consider their technology, which also makes a sour compression for NOx and SOx bed. So this is one of the leading technology when you want to capture CO2 in oxy-combustion plants. Regarding the thermal integration, also this factor is very important because you want to reduce the cost, but also you want to maximize the efficiency of your plant. So you do need to consider the thermal integration between the different units of your plant, and especially was taken into account the thermal integration between the air separation unit and the compression and purification unit. Other key design features, as we said, regarding the compression and purification unit, we considered and we cooperated with Air Products. The Air Products process is basically based on two key units, the warm main and the cold main. So in the warm main, when you have the first cooling of the flue gases with a direct contact with the water, then you go to what we have already said, the sour compression section. So there is a compression of the flue gases, and there is a removal of SOx and NOx by using contact with water and oxygen. And SOx and NOx are transformed into sulfuric acid and nitric acid. Downstream this unit, you can then go to a TSA for the removal of the residual water, and then you go to the cold tank, which is an auto-refrigerated cycle, which makes the refrigeration of the flue gases without using any refrigeration cycle, because it uses the Joule-Thomson effect of the expansion of the gases produced in the process. And the configuration of this unit very much depends on your purity requirement on the CO2. In this case, we said that we had a purity requirement on the maximum content of the oxygen, 100 ppm. And for this reason, we had to use distillation columns of the flue gases in order to meet the CO2 purity requirement. But also, you see that you may also use membranes. So what the Air Products is licensing are the freeze membranes. And if you use these membranes, you may achieve very high CO2 capture rates in the range of 98-99%. So let's focus a little bit on the sour compression section. We said that you have an initial compression up to 15 bars, and you can, at this point in time, by making a contact with water, you may remove the SOx. But what happens in the column is that because of the oxygen and because of the water in this condition of 15 bars, the first reaction, so NO is becoming NO2 only in a few seconds. And then it happens that there are the other reactions in order to produce sulfuric acid. And you may achieve very high SOx removal rates in the range of 98 to 99%. Then we got to the NOx removal part, and before going to the column, there is a second compression up to 30 bars. And by contacting the flue gases at this pressure with water, then you have these two reactions that you may pass from NO2 to nitric acid very easily. And all these acids are removed from the bottom of the process. We said that flue gas pressurization was a key factor that has been taken into account in the design of the plant. We said, why FGD? FGD, as we said, is is not required to reduce SOx emission from the plant, because in the process is removing the SOx. But SOx FGD is required in order to keep in the furnace a low content of SOx in order to avoid very high corrosion in the boiler. And this is the value we consider as a design factor. So, what type of FGD and where to place the FGD? This is an important factor. So, we have seen that for very low sulfur fuels, and that means in the range of 0.5 percentage points, FGD is not required. So, there's no need of FGD. For coals which have a medium content of sulfur, from 0.5 to 2%, FGD is required. And you can install your FGD on the primary cycle. Primary cycle in terms of flow rate is much lower than the secondary cycle. And or you can also install the FGD on the secondary cycle, but in this case, you need to have a lower removal efficiency, higher removal efficiency if you install in the primary cycle. For coals which have a very high sulfur content, greater than 2%, then you have to install your FGD either on the secondary cycle or on the total flue gas flow, and that means, of course, higher capital cost. So, which technology to be considered for the FGD? We said that when you install the FGD on the primary cycle, and remember, this is the block flow diagram of the plant, this is the primary cycle, lower flow rate, but also this lower temperature in the process. So that means that in this case, you cannot use a wet FGD, but you have to consider the use of a dry FGD, and this is what we consider in our work. And particularly we consider a circulating fluid-based scrubber with light-sorted injection. But if you install the FGD on the secondary cycle, then you may consider wet FGD. So you may enter at the proper temperature in the system. And in this case, you have to have limestone injection, with the advantage that in this case you may produce some soluble yips, which could be sold into the market if the market exists in your plant. The advantage of the FGD on the primary cycle is that you can use a smaller FGD, and that means you save some gaps from your plant. And because the bigger FGD is required in the secondary cycle, with the advantage, of course, if you change your feedstock, and for example, during the operation of the plant, you use a coal with higher sulfur content, the wet FGD in this case allows you to have higher operational flexibility of your process. Okay, so thermal integration, as I said, was very important, and we considered to have a maximum heat recovery from the condensate by preheating the condensate of the power liner, but also by preheating the boiler and the boiler feed water. And we tried to maximize the heat recovery, but always keeping in mind an economic approach to the problem. This allowed us to increase significantly the net electrical efficiency of the plant. We also considered some thermal integration for the preheating of the inert gases before venting, trying to reduce as much as possible the use of steam coming from the power plant in order to increase the power production from the steam turbine. But let's look at the performance. And here is a comparison between the plant with oxy-combustion and the plant using a standard technology for power production. So you may see, I want to highlight as I said, we consider state-of-the-art technologies, and that means that for a conventional plant without CCS, we may achieve a net electrical efficiency HB basis in the range of 44%. But look at when you consider oxy-fuel combustion, your net electrical efficiency becomes 35.7%. So that means that you lose a lot on your net electrical efficiency. You lose almost 8.4 percentage points, which is a very, very significant loss of your efficiency. Economics. This is a graph showing the total plant cost. Again, this is a comparison with a standard plant without CCS. You may see that here they are not Indian bases. We are talking about standard European conditions. So let's say that we are very interested in the delta, in the delta performance and delta costs between the plant, not in the absolute values. So nevertheless, so if you consider a standard plant without CCS, the total plant cost is in the range of 1,500. But if you have oxy-fuel combustion, you go up to 2,300. So again, it's a very important figure because the total plant cost is increasing by a factor of 54%. 54% added to your total plant cost. And why? The main reason is here. The main reason is basically the introduction of the compression and purification unit, which is the violet band in the graph, but also the air separation unit. So both units are very capital intensive, and basically the addition of these two units is explaining the additional 54%. But going deeply on the economics of your project, as I said, we used some standard European conditions, and for example, we considered 2.5 as a coal cost, euro per gigajoule, and discount rate of 8%, 25 years operation of the plant, and so on. So, these are some basic assumptions in order to estimate the levelized cost of electricity. So again, in the graph, there is the comparison between the conventional plant without CCS and the plant with CCS. You may see that we have, for the conventional plant, a levelized cost of electricity of roughly 52 euro per megawatt hour. In the oxy-combustion plant, you achieve almost 92 euro per megawatt hour. So that's very important. And why is it such a high cost? Again, because you have an additional cost. We also consider the cost for the transportation and the storage. But mainly you have this higher cost because of your higher capital cost of the plant. Using these figures, so what is the cost for capturing CO2 at your plant? This is the cost. This is the CO2 avoidance cost. You may see here it's very high. So if you want to capture CO2 at your plant, European basis, you need to consider 61 euro per each ton of CO2 that you capture in your plant. As a sensitivity case, I said that I also consider the capture of the CO2 at very high level, so in the range of 98-99%. That's why we consider the installation of the freeze membranes supplied by electrodes. So some key parameters only, and this is a comparison between the 90% captured and the 98% captured. I want to just highlight that if you want to go from 90 to 98, then you lose another part of your efficiency, which is Not very much indeed, because it is only 0.4 percentage points. And also the capital increase of your plant is not very high, because it is only 25 million only. It is in the range of 1% of your total plant cost. So some conclusions, just trying to be on time. What we have seen in the presentation, we've seen that as of today, plant net electrical efficiency of 35.7% can be achieved with a CO2 removal rate of 90%. So as of today, with the technologies which are available today, this can be achieved. We also have seen that the oxy-combustion technology is particularly suited to make near zero emission of CO2 to the atmosphere. We are thinking that CO2 capture provides the best economics, but only for the CO2 emission cost, which is higher than 61 euro per ton. And all the considerations I did today are valid. We selected the conventional PEC boiler, but all these considerations also are applicable to the CFV technology, and I will go into very much into details in this afternoon session. Thank you very much for your attention. Thank you.